Hello guys, this is me from Chalk and Duster, and today I am back with another video on this topic, linear algebra part 2 here. Here we will discuss basis, dimension, linear independence of vector and linear transformation and rank nullity theorem. In the previous video we have learned about vector space, subspace, group theory and abelian groups. If you have not seen that video, make sure that you know these topics here. So here we start with this linear independence of vector. This set of vector v1, v2, vn, they are said to be linearly independent. If this equation is equal to 0 implies that all of the ai's, that is a1, a2, a3, all of them must be 0. Then only the set of vector v1, v2 is said to be linearly independent here. Okay, that is all I, this must be equal to 0. This implies that this set of vector t, this is linearly independent. Okay, if either of ai, this is not equal to 0, implies this set of vector t, this is linearly dependent. Okay, so our first example here, to check whether this set of vectors is linearly independent or not, what we do is we multiply this with the coefficients here, alpha, beta and gamma respectively. Alpha plus beta 3, 5, 7 and gamma here 5, 9, 3. Okay, and what we do is we compute it with this 0 matrix of the same order here, 3 into 1. So what happens here is just form a system of linear equation. Alpha plus b3 beta plus 5 gamma, this is 0. 2 alpha plus 5 beta plus 9 gamma, this is 0, and 3 alpha plus 7 beta plus 13 gamma, this is again 0. Solving this system of linear equation, what we get is alpha is equal to 2, beta is equal to 1 and gamma is equal to minus 1. So what we see here is we can represent the third vector, this third vector or third matrix, in terms of these two matrix here in this form. Okay, so what happens is these three vectors were linearly dependent. Why dependent? Because the third one depends on the first two. So the span of these three vectors is same as these two vectors here. Okay, we can do one more thing. Okay, let me show you with this example to check whether these three polynomials are linearly independent or dependent. Again, we do here is alpha times px plus beta times qx plus gamma times rx. This we equate with the 0 polynomial, that is 0x square plus 0x plus 0. So what we will do is we will equate the respective coefficient of x square, x and x to the power 0, and we will compute the value of alpha, beta and gamma. This is the first approach by which we can solve this. And another approach is make a matrix, basically the coefficient matrix here, like this 1, 3, 2, 3, 1, 2, and here 0, 2, 1. Okay, then what you have to do is you have to compute the determinant of this matrix A. So to compute this, what you do is you perform this operation, R2 minus 2 times row 3. Okay, so can do here, insert some space. So performing this operation here, we get this 1, 3, 0, 3 minus 4, that is minus 1, here minus 3, there is 0, and again this 2 to 1. So what we get determinant as? We get determinant as 1 into minus 3 plus 3, that is equal to 0. As determinant of this matrix, coefficient matrix is 0, implies these three polynomials were linearly dependent. Similar approach you can have for this matrix. You can find the determinant of the matrix formed by these three column vectors here, and if the determinant that is 0, then this we are linearly dependent, else they were linearly independent. Okay, then we define the basis. What a basis is? So if V be a vector space and as this is equal to a subset of this vector V, then S is a basis of V. For these two conditions that must be true. That first one, S spans V and S must be linearly independent set of vectors in V. Okay, actually let me make you show by some example here. Suppose the coordinate system here. So coordinate system in 3D. What happens here is this coordinate system is set of all the points here in 3D plane, all the xi's, yi and zi such that x, y, z these are real number here. Okay. So how we calculate basis as basis is 0, 0, 1, 0, 1, 0 and 1, 0, 0 by linear combination of these three vectors here in this way as alpha 0, 0, 1 plus beta 0, 1, 0 and plus gamma 1, 0, 0. What can say as gamma beta alpha, that is we can represent all the points in 3D plane by these three vectors only. So this is a subspace here, and what it does, it spans V, that is it can represent all the point here, and furthermore these three vectors they are linearly independent as one can't be represented as linear combination of other two. Okay. So here is the statement here, the same which I said. Let S is the basis for V, then every vector in V can be uniquely written as linear combination of vector in S. Same in this way here. So okay, after basis we to define a standard basis. A standard basis, like for example in case of 2D plane it's 1 0 and 0 1. In case of 3D it's 1 0 0 0 1 0 0 0 1. The same which I used here. Basically it's a combination of zeros and ones. Suppose a matrix of order 2 by 2. So its elements be like this A, B, C, D. So you can obtain all the matrix of 2 by 2 order by linear combination of this 4 matrices here. So here in this way we define a standard matrix, standard basis here. Okay. And after that after basis we will define here the dimension. So what is the dimension is the dimension of vector V is the number of vectors in the basis. Number of vectors V in basis means here in 3D, in case of the 3D plane, what happens here is we are having 3 vectors in this basis, so its dimension is actually 3. And in case of 2D we need 2 linearly independent, this is standard basis here, so its dimension is 2, and in this case its dimension is 4. Okay. Here, okay, it will make you show by some example here. Suppose you have to find the dimension of subspace in the fourth coordinate here, spanned by the set of these four vectors here, and we have to find its basis. So how do we calculate it as? Consider 4 constants here, alpha, beta, gamma and delta, and you do linearly combine these vectors here. Beta 0 1 0, gamma 1 2 0 1, and finally delta 0 0 0 1, and equate this with this 0 vector here. So what happens here is alpha plus gamma, this is 0, and beta plus 2 gamma, this is 0, and here what else? It will be gamma plus delta, this is 0. So if you suppose that gamma this is equal to some phi, then we can represent as alpha, this is minus phi, alpha is minus phi, beta is minus 2 phi, gamma itself as phi, and delta again is minus phi. So what we see here is if we put the value of phi as 0, then all these terms alpha, beta and gamma, alpha, beta, gamma and delta, they all tend to 0. That is by putting 1, all 3, the rest 3, that turns to 0. So its dimension is basically 3, and since its dimension is 3, its basis can be any of these 3 vectors. You can choose any of these 3 vectors out of this 4, and the fourth one can easily be represented in terms of other three. So its basis, that would be 1 0 0 0 1 0 0 and 0 0 0 1. Okay, do remember one point, that basis is not unique. Standard basis is unique, but basis, that is not unique. There may be infinitely many bases. Okay, and consider this example here. So again, what we have to do in this example is we have to parameterize, or we have to find the parametric solution here. Suppose your D, this is equal to some alpha, then D is equal to alpha, and C, this is equal to beta. Then your A, this will be minus of alpha plus beta. Your B, this will be minus of alpha, C is beta again, and D is alpha. So you can write this 4 points A, B, C, D as minus of alpha plus beta, minus alpha, beta and alpha. So what you do in first case is divide this by alpha. So this is minus 1 plus beta upon alpha, minus 1 beta upon alpha and 1. And what you do is just make this beta by alpha 0. So what else is left is minus 1, 0, 1. In second case, what you do is you divide it by beta here. So it's 1 minus alpha upon beta, comma minus alpha upon beta, comma 1, comma alpha upon beta. In this case, again you turn this alpha by beta as 0. What else is left is 1, 0, 1, 0. So these two are the bases. Minus 1, 0, 1 and 1, 0, 1, 0. Okay. So this you can consider as a standard method to find the basis. What you have to do is you have to find the parametric solution and then divide by one of the parameters here and make this 0 in the first case. In second case, divide by another parameter and make this 0. If there is third parameter, then divide by the third parameter and make this 0. So whatever the vectors you will get, that is the basis. Actually, if you have read from your teachers or somewhere else, so you have to calculate the basis by your own. There is no any method as such. Basically, you have to guess. But by this method, you have not to guess. You can find the basis here. Okay. Then our next topic is linear transformation. Linear transformation is same as functions, that is domain, codomain. Basically, just like a machine. If you input some data here, the data input, and this data is processed, and you get some output. Same way it works here. Linear transformation. So linear transformation is what? It's a function that carries the element of the vector space U to the vector space V. The element of the vector space U, that are called domain, and the element of vector space V, those are called codomain. And so two properties here. Basically, a function is said to be the linear transformed one if and only if transformation of the function of u1 plus u2, that we can separate as function of u1 plus function of u2. And second one, this property, the transformation of au, where a is a constant, then you can put this a out of the transformation and this one is left. So what follows from here is, if you put a is equal to 0, this implies t of 0, this is equal to 0 into t of u, t of 0, which is equal to 0, which implies t of 0 is equal to 0. So one of the most important cases, 0, 0, this must satisfy the case of linear transformation here. That is, this is an integral part. If you have to check, the first step is you must check here whether 0, 0 satisfies it or not. Okay. So linear transformation, okay, don't confuse that linear transformation are some linear functions like y is equal to some x by 2. This is a linear transformation, no doubt, but other function can also be linear transformation. Okay. Suppose here is the case of differentiation. Okay. Differentiation. What you do is, if you have to differentiate with respect to x this polynomial function, x cube plus x square plus x plus 1. So what you do is you distribute them as differentiation of x cube plus differentiation of x square. Okay, let's take here some 9x, okay, instead of x 9x here, and differentiation of this 9x and then differentiation of 1. So this is basically 3x square, this is 2x, and you can put this 9 out of this differentiation function here, and you can write this as d upon dx of x and plus 0 here. So what you say is the first condition is satisfied here, and second condition that is also satisfied here. So differentiation is a case of linear transformation. Okay, hope you have understood the linear transformation. And you can also see this, the differentiation of 0, this is nothing but 0. So this case, this condition is also satisfied here. Okay, hope you have understood what a linear transformation is. After linear transformation, we will come to the rank nullity theorem, and before discussing rank nullity theorem, we will first discuss here. Okay, we will first discuss here the case. What is this kernel of T? What is this rank of T? If you have read the equivalence relation, then this is the same as the equivalence class. Okay, basically all this here, what was the case here in the linear transformation, that 0, 0 satisfies here. So what is kernel of T? Kernel of T is basically the set of all V such that transformation here is 0. Okay, suppose the case this x square minus 2x plus 1, this is 0. X square minus 2x plus 1 is equal to 0. So this is what? X minus 1 square. So if we write for value of x is equal to 0, its value is 1. For value of x is equal to 1, this is 0. For 2, this is 1. For 3, this is 4, and like so on. So what will be the kernel of T? V such that T of V is equal to 0, that is for 1 this function is 0. So this is basically 1 only. And suppose some other function is there like x minus 2 into x minus 3 into x minus 4, this one. Then what is the kernel of T? It will be 2, 3, 4. Means set of all points where the function itself is 0. Okay, so this is basically kernel of T, and rank of T is basically the range. You can consider it the range. So all the numbers, this will come 1, 0, 1, 4, and so on. Hope you have understood this kernel and rank here. Basically this one, the dimension of null space of A, this is referred to as nullity of A. And null space here, this is same as kernel, null space by, because 0 is there, this one. So basically you have to find this dimension of kernel of T plus dimension of rank of T, this is dimension of V. This is basically the statement of the rank nullity theorem. Okay, dimension of rank of T here. Consider this matrix here. So what you have to calculate is rank and nullity. So how will you calculate its rank and nullity? See here. This one is row 1, this is row 2, and this is row 3. If you observe it carefully, then we can write row 3 as 2 times row 1 minus row 2. 2 times 1, that is 2, 2 minus 3 minus 1, 2 times 1, 2, 2 minus 4 minus 2, 2 is a 4, 4, 4 minus 1, that is 5. So you can find it here. So what we say is that row 3 that can be expressed in terms of row 1 and row 2. So what happens is dimension of rank of T, that is 2, and as per rank nullity theorem, dimension of rank of T plus dimension of kernel of T, that is dimension of V, and dimension of V is nothing but number of columns. Okay, so dimension of rank of T, that is 2, plus dimension of kernel of T, that we have to find out, and number of columns here is 1, 2, 3, 4. So 4. This implies dimension of kernel of T, that is 2, and dimension of kernel of 2 is nothing but nullity. So nullity is 2. So what we found as rank, this is 2, and nullity, this is 2. So in this way we can compute rank and nullity. Hope you have understood this rank nullity theorem. So finally write what was the rank nullity theorem. This is rank of T plus nullity of T, and this is equal to dimension of V. Okay, let me consider one more example here. Suppose the question is, for the set of vectors x1, x2, where x1 is 1, 3 transpose, and x2 this is 4, 6 transpose. Obviously this vector is in second dimension, that is IR square. So what you have to do is you have to find the transformation from the IR square to the IR cube, that is from the second dimension to the third dimension, such that T of x1, transformation of x1, this is minus 2 to minus 7 transpose, and T transformation of x2, this is equal to minus 2, minus 4, and minus 10 transpose. So what you observe here is that this is a matrix whose order is 3 into 1 matrix. This is of order 3 into 1, this one, and this both are of order 2 into 1. So T, the important condition of matrix multiplication is that this T, its dimension must be 2 into 3, such that when these two matrices get, when we multiply these two matrices, the dimension must be 3 into 2, such that when we multiply this matrix with this matrix whose dimension is 2 into 1, so that it produces a matrix of dimension 3 into 1. These two must be similar. So let us suppose our matrix as of order 3 into 2. This is A, B, C, D, E, F. Okay. So first what we do is, first we multiply this with this vector. What was x1? x1 was 1, 3 transpose here. So we multiply this with 1, 3, and what we get is minus 2 to minus 7. And in the second case, what we do is A, B, E, C, F. We multiply this with 4, 6, and what we get is minus 2, minus 4, minus 10. Okay. If you will solve this matrix, okay, let me do one for you. Like this is A plus 3D, this is equal to minus 2, B plus 3A, this is equal to 2, and C plus 3F, this is equal to minus 7. Similarly here 4A plus 6D is equal to minus 2, 4B plus 6C, this is equal to minus 4, and 4C plus 6F, this is equal to minus 10. When you will find the value of this, equations are here, okay. Express as equation 1, equation 2, equation 3, equation 4, equation 5, equation 6. So from 1 and 2, what will you get as A is equal to 1, D is equal to minus 1. Similarly for other values, B is equal to minus 4, P is equal to minus 4, E this is equal to 2, and C this is equal to 2, and F is equal to minus 3. So this is how you calculated your matrix here: 1, minus 1, minus 4, 2, 2, minus 3. So this was your transformation here, and you have to find the same. Hope you have understood what a transformation is and how to solve questions. Thank you so much. And if you are having any doubt, feel free to ask in comment section. Thank you so much.